Hi everyone, my name is Kangdon. This is my final report of the project for CS 898BA. The project is automated detection and classification of 3D printing failures using image processing and deep learning. This is a reproducible scratch versus retrain study. So print failures like spaghetti, layer cracking, over extrusion, shrinking, and warping waste filament machine time and currently requires someone to babysit the printer. My final objective was fourfold: localize defects with bounding boxes, classifying the defect type, compare a one-stage and two-stage detector head-to-head, and evaluate whether image processing and training system decision actually help. So my design rests on four ideas. One stage YOLO style detection for speed, faster RCNN as a two-stage alternative with stronger localization, COAHE and edge processing for domain-specific contrast, and pre-training literature, which sets my expectation for how much pre-training detectors should outperform scratch ones. I implemented two detectors from scratch, a fast one-stage YOLO26 style detector and a faster RTN with a resonance style backbone, FBN, RPN, all ILI, and per class NMS. Before I trust any result, I had to fix data. My final dataset covers five classes across 3,421 records and 823 source groups split into three group folds. I found the original exported split had duplicate contain overlap and annotation disagreement, so I excluded the public candidate test split entirely. Every result I report is grouped by date estimate, not an independent deploy claim, which is strange for this project. I treated image processing as something that's not assumed would help. I compared three variants: RGB baseline, LEB plus COHE, and LEB plus COHE plus Kenny edges. The finding LEB plus COHE actually improved detection performance over the raw RGB baseline. But adding Kenny edges on top didn't improve the result any further, so that combination was rejected. Beyond the reprocessing itself, the biggest domain engineering contribution was the label format repair, strict validation, and audit underneath it all. Here's a full pipeline. Image and label go through a dataset audit, then branch into baseline RGB, LAB, COHSE, LAB, COHE can then fit into YOLO or faster RCN, and then each reproducing loss, MAP, precision recall, and per-class metrics. One important disclosure: this is a system comparison, not a capacity matched one. My YOLO26 has about 2.66 million parameters. My faster RCN has about 28.86 million parameters. To keep this reproducible, I fixed the seed at 42, use three group folds, train at 960 pixel resolution, and evaluated precision and recall at 0.25 confidence threshold. I rank models by MAP 50 and MAP 50 to 95. Use a confusion matrix and never touch the public candidate tested for optimization. The best checkpoint was selected by validation MAP 50 while validation loss remained the controller signal. That kept the checkpoint selection aligned with the metrics that I actually report. This slide show that so what actually moved the needle as a decision timeline rather than a giant research. For YOLO26, an AP50 time from 0.0615 through 960 pixel resolution, classware NMS, the one-to-many inference branch, and MAP15 based checkpoint selection, ending at 0.1586. For faster RCNN, the jump is more dramatic, from 0.0075 in a pre-repair diagnostics run up to 0.3258 after an RPN positive supervision repair, checkpoint selection, and a warm-up call sign schedule. That RPN fix wasn't ordinary tuning, it was a correctness repair for a broken training signal. The table is my evidence that this was a systematic optimization, not a random experimentation. Every treatment was tested and explicitly accepted or rejected. One-to-many inference and MAP50 checkpoint selection was accepted for YOLO26. MAP50 checkpoint also accepted for faster RCMN. The cosine schedule was retained cautiously for faster RCMN, and things like P2 for small object path, DFL box regression, ImageNet transfer, flip CTA, EMA, and online photometric augmentation were tested and rejected because they didn't help under this protocol. The full decision report live in project work log.md. Here's the main result like my fresh faster RCNA framework call sign schedule, which point 3258 MAP50 and point 1239 MAP50 to 95. My scratch YOLO26 with a fixed learning rate, which point 1886 MAP15 and point 0512 MAP50 to 95. Faster RCNN was my strongest custom scratch detector by rank AP, while YOLO26 remained the lighter, faster one-stage option. Again, these are validation selected. Group CV estimate not independent final test score. Breaking down by class, both models struggle badly on spaghetti, which is a diffuse hard-to-box defect. But faster RCNN pulls substantially ahead on layer cracking, overextrusion, changing, and warping. Diffuse defect emit multiple defensible box boundaries, which limit box level agreement, and class imbalance plus annotation variation explain the instability on rare classes. So now this a honest comparison against practical references. My scratch model sit well below Coco pre-trained YOLO26 and YOLO11, both around 0.46 to 0.48 MAP50 versus my 0.16 and 0.33. But the pre-trained system differ from mine in retraining, loss implementation, augmentation, reprocessing, optimizer behavior, and NMS. This is a practical value comparison, not proof that my Scratch architecture is inferior on a level playing field. So now for the virtual demonstration, I open the project repo in VS Code for a live demo here. Please have a look at it. Hi, this is a live demo for my project, testing on 4 images. I'll test the best model for my YOLO26 and faster RCNN using this command. So for the first image, you can see that even though both models can detect spaghetti's error, they miss one out of two error. For the second image, you can see that faster RCNN here is predict kind of well when it can see over extrusion and layer cracking, even though it still missed some. But for YOLO26, it missed all the layer cracking error here, and also its Foley's predict changing error over here as well. For the third image, the ground truth shell changing and over extrusion, which you can see faster RCNN can predict those. There are one false prediction here, but for YOLO26, there are a lot of false prediction here, which is layer cracking, changing over here, even though there was no, and then warping here. For the last image, there was warping error in this image. Faster RCNN cannot predict any, and YOLO26 once again over predicts everything. It It follows predict changing, layer cracking, warping, over extrusion here, and it's also predict correctly warping error over here. So to wrap up, I built two full custom detector pipelines including image processing, label normalization, trick validation, proof CV, NMS metrics, and a practical pre-trained reference for demonstration. The limitations are sparse minority classes, the field defect boundaries, some remaining annotation disagreement. We use our validation flow for model decisions and no clean external test set. Going forward, I would create more independent data sources, a certificate annotation, reserve a truly parallel test set, and if the goal shifted to practical performance, retrain these exact architecture before fine-tuning. The main takeaway is a reproducible, evidence-driven study that separate implementation versus from valid improvements, negative results, and practical values for large-scale retraining. This is the references for my project, the YOLO26 paper, the original FASTA RCNN paper, the COAHE paper, and the data set I used for the project. Thank you so much for hearing.